Welcome to Section 1, Lesson 1. Today we look at the number line. You have seen this line since you were a child, but in this lesson we look at it the way a mathematician looks at it. The whole point of this lesson is to give you a single picture that the rest of algebra will sit on top of, so let us take it slowly and build it up step by step. First idea on the board. Every real number has exactly one home on the line. Not approximately, not most of the time, exactly one home. Each integer, each fraction, each square root, even pi and e, every single one of them has its own one position. No number is missing from the line, and no two numbers ever share the same spot. Second idea on the board. Pi, the square root of 2, and the constant e all live on the same line. Right next to the integers and the fractions you already know, they are not separate kinds of numbers that live somewhere else. They are right there on the line with everything else, and we will see exactly where each one sits. Third idea on the board. Once every number has a position, three useful things come for free. First, ordering. The number on the left is always the smaller one. Second, distance. The gap between two positions is always positive. Third, intervals. We can describe an entire stretch of the line in one short piece of notation. That is the picture this lesson builds in 7 small steps. Here is the number line, a horizontal line with arrows on both ends and a dot labeled 0 in the middle. The arrows tell us the line never stops in either direction. To the right of 0, numbers grow larger, 1, 2, 3, and onward. To the left of 0, numbers grow more negative, -1, -2, -3, and onward. 0 itself is the reference point that everything else is measured from. First, we add the integers. Tick marks and labels appear at -5, -4, -3, -2, -1, then 1, 2, 3, 4, and 5. 11 evenly spaced positions in total, including 0. Each tick is exactly one unit from its neighbor. The integers are the simplest family on the line, but notice the wide gaps between them. Those gaps will get filled in by the next two families. Now the fractions, also called the rational numbers. A blue dot lands at 1/2, halfway between 0 and 1. A second blue dot lands at 3/4 of the way from 0 to 1. A third blue dot lands at -3/2, sitting between -1 and -2. A fourth blue dot lands at 5/3, just past the 1. Every fraction you can write with whole numbers on top and bottom has its own exact position somewhere on this line. Now the irrationals. These are numbers that cannot be written as a clean ratio of two whole numbers. The square root of 2 appears as a yellow dot at 1.41, just past the 1. Pi appears as a pink dot at 3.14, just past the 3. The constant e appears as a green dot at 2.7, between the 2 and the 3. These three numbers are infinite, non-repeating decimals, and yet they each sit at a single fixed point on the line. Watch the density of the line. Many small dots fill in the gap between 0 and 1. The line is dense, which means between any two numbers, no matter how close together they look, there is always another number squeezed in between. You can never zoom in far enough to find a stretch of the line that has no numbers in it. This is why the number line is described as continuous. Together, all of these dots are the real numbers. Every point on this line is a real number, and every real number sits at exactly one point on the line. Integers, fractions, irrationals, and uncountably many others, each one with its own address. From here on, when we say a number, we mean a position on this line. That single picture is the foundation for everything else in algebra. Here are 6 numbers across the top of the screen. -2.5 pi, 20, 2/7, the square root of 10, the constant e, and negative square root of 3. Below them, the number line, blank and ready. We will place each one at its exact position, then read the final order from left to right at the end. The reason this matters is that converting any number to a position on the line is the most important skill in this entire section. negative 2.5 lands halfway between negative 2 and negative 3. We do not need to do any extra arithmetic for this one, because the decimal already gives us the answer. A blue dot appears halfway between the two ticks for negative 2 and negative 3, with the label negative 2.5 just above it. Negative square root of 3 is about minus 1.73 because the square root of 3 by itself is 1.73, so negative root 3 sits between minus 1 and minus 2, but closer to the minus 2 side. A pink dot lands there with the label negative root 3 approximately equal to negative 1.73. The constant e, also called Euler's number, is about 2.718. So E sits between 2 and 3, but much closer to 3. A green dot lands there with the label E approximately equal to 2.72. Pi is about 3.14, so pi sits just past the 3 on the right side of the line. A pink dot lands there with the label pi approximately equal to 3.14. 22 over 7 equals about 3.143. That is almost the same as pi, but not quite the same. A yellow dot lands almost on top of the pink pi dot with the label 20, 2 over 7 approximately equal to 3.143. A small caption underneath reads, almost on top of pi but not equal. This tiny gap between 20, 2 over 7 and pi is one of the famous near misses in mathematics. The square root of 10 is about 3.16. Because 10 sits between 9 and 16, the square root of 10 sits between 3 and 4, and a more careful estimate puts it at 3.16. A yellow dot lands just to the right of 20, 2 over 7, completing a tight cluster of 3 numbers between 3 and 3.2. Now the ordered sequence of all 6 numbers read left to right off the line. Negative 2.5 sits the furthest left, then negative root 3, then e, then pi, then 22 over 7, then square root of 10. The ordered list appears in cyan at the bottom of the screen. Reading the order of the line takes the work out of comparing decimals by hand. Take 2 numbers on the line. The number a equals negative 2, marked by a blue dot on the left side. The number b equals 5, marked by a blue dot on the right side. We will compute the distance between them and then describe 4 different ways to talk about the entire stretch of numbers between them. To compute the distance from a to b, draw a yellow segment along the line from negative 2 to 5 and a brace below the segment pointing down. The brace makes the gap easy to see. Distance does not care about the direction of travel from A to B or from B to A. It only cares about how far apart the 2 positions sit on the line. The distance is the absolute value of negative 2 minus 5, which equals the absolute value of negative 7, which equals 7. The yellow label below the brace reads vertical bar, negative 2 minus 5 vertical bar equals 7. The 2 numbers are 7 units apart. The same answer comes out if you reverse the order. The absolute value of 5 minus negative 2 again equals 7. Distance is always positive, no matter which direction you measure it from. Now 4 interval forms. The first is the closed interval from negative 2 to 5, a blue segment running along the upper part of the screen, with solid blue dots at both ends. The label above the segment reads bracket, negative 2, 5 bracket. The square brackets on both ends mean both endpoints are included. The set contains negative 2, 5, and every number in between. Next, the open interval from negative 2 to 5. The blue segment fades out, replaced by a yellow segment with hollow yellow rings at both ends instead of solid dots. The label reads parenthesis, negative 2, 5, parenthesis. Both round parentheses mean the endpoints are excluded. The set contains every number strictly between negative 2 and 5, but not negative 2 itself and not 5 itself. Then the half-open interval. The yellow segment fades out, replaced by a green segment with a solid green dot on the left at negative 2 and a hollow green ring on the right at 5. The label reads bracket, negative 2, 5, parenthesis. The left endpoint -2 is included because of the square bracket. The right endpoint 5 is excluded because of the parenthesis. The shape of the bracket on each end is the entire rule. Finally, the ray to -infinity. The green segment fades out, replaced by a pink segment running from -2 leftward, ending in an arrow pointing further left, with a solid pink dot on the right at -2. The label reads parenthesis -infinity, -2 bracket. -2 is included because of the square bracket on its side. The infinity side always uses a parenthesis because infinity is not a real number you can land on, so it can never actually be included in the set. 3 common mistakes that trip up almost every algebra student when they first work with the number line. Each one comes from forgetting that position on the line is what matters, not just the digits in the number itself. We go through them in turn, and we say out loud the right way to think about each one. Comparing negatives. A student writes that -3 is greater than -1 because 3 is greater than 1. That comparison is wrong. On the number line, -3 sits further to the left than -1, and on a number line, further left always means smaller, so -3 is less than -1. The simple test is ignore the sign, look at the position on the line, and the rightward one is the larger. Reading fractions. A student writes that 1/3 equals 1.3. That decimal is wrong by quite a lot. 1/3 is 1 divided by 3, which equals about 0.333 repeating. So 1/3 sits between 0 and 1, much closer to 0. The numerator and denominator do not just sit next to each other as decimal digits. You have to actually divide. Reading bracket shapes. A student sees the interval written as bracket 2,5 parenthesis and assumes the whole thing is included. That assumption is wrong. The square bracket on the left means the 2 is included. The parenthesis on the right means the 5 is excluded. The shape of each bracket sets the rule for that endpoint, and the 2 endpoints are independent of each other. The number line is not only a teaching tool from algebra class, it shows up everywhere measurement is done. Here are 4 real-world places you have already seen the same idea, just under a different name. Once you spot the pattern, you start seeing the number line in places you never noticed before. On a thermometer, temperature is read along a vertical number line. 0 marks the freezing point of water in Celsius. Numbers above 0 are warmer. Numbers below 0 are colder. The position on the scale is the temperature. 20 degrees above 0 feels warm. 20 degrees below 0 feels freezing. The position is the meaning, exactly like the number line we built today. On the pH scale in chemistry, acidity is read on a number line from 0 to 14, with 7 sitting in the center as the neutral value. Lower than 7 means the solution is acidic. Higher than 7 means it is basic. Lemon juice sits near pH 2. Pure water sits at pH 7. Household bleach sits up near pH 12. Every solution has one exact pH, just like every number has one exact position. On a historical timeline, dates spread to the left of a chosen reference year as the past and to the right as the future. The Roman Empire sits to the left, the moon landing sits to the right of the year 0. The line lets you immediately see what happened before what and how far apart any 2 events sat in time. The same line used for calendar years. In finance, profit and loss are tracked on a number line centered at 0. 0 is the break-even point. A position to the right means profit. A position to the left means loss. The distance from 0 tells you how big the gain or how big the loss is. A trader staring at a daily returns chart is reading a number line. Same line, different name, same logic. 3 things to take with you from this lesson before we move on to the next one. Each one will come back many times in later sections, so make sure each one feels solid before you continue. First, every real number has exactly one position on the number line. Integers, fractions, irrationals, and any other real number you can imagine, Every single one has a single, exact home on the line, and no two real numbers ever share the same address. From now on, when we talk about a number, we mean a point on this line. Second, comparing two numbers means comparing their positions on the line. Whichever number sits further to the right is the greater one. To find the distance between two numbers, take the absolute value of their difference, which gives a positive answer no matter which order you write them in. Third, intervals describe a stretch of the line. Square brackets include the endpoint. Round parentheses exclude it. Mix and match the brackets as needed. Coming up next, we use the number line to drive every operation in arithmetic in the lesson called Order of Operations. See you there.